So in the first section of this chapter, we started talking about conic sections, and we were looking at ellipses. And now we're going to look at something called a hyperbola. We had actually drawn a picture last time, and essentially if you have your two cones like this, if you took a plane and cut through your cones like this, and then looked at what you got, you would essentially get a curve like this and a curve like that on the bottom. And that's going to be a hyperbola look like that. It kind of looks like that. One thing I would stress before we actually do this, when you look at it really quickly, that looks like two parabolas, one on top of another. They're not actually parabolas. The curvature of them is different. So just make sure they look similar to it, but mathematically they are different. But we just want to kind of do what we did with ellipses, look at the graph, look at the equation, and kind of figure out what's going on. Much like with ellipses, there's a lot of algebra involved in doing these. Some of it is in your book, and I'll kind of leave that for you to work through in your book. There's a few homework problems on it. And I'll just kind of work through a few problems with the definition to make sure we understand how to do it. So first off, the general equation. The equation is x squared over a squared minus y squared over b squared equals 1. And if you look, it's essentially identical to the ellipse equation, except that for the ellipse equation, this was a sum. And we remember from the definition of ellipse was all points in the plane, the sum of whose distances from two fixed points was a constant. And if we actually look at this right here, for a hyperbola, the definition is the set of all points in the plane such that the difference between a point and two fixed points, the foci, is a positive constant, which is kind of where this comes from. The ellipse is a sum. You add up the distances from the foci. The hyperbola is a difference. You subtract them. So, well, in lieu of that, when we did our equations for ellipses, we essentially said the A and the B told us where our major arc and our minor arc were. They told us the orientation. And it didn't really matter how you chose to write it because it was a sum. Here, it actually will matter because this is a difference, which means you can either write x squared over a squared minus y squared over b squared equals 1, or y squared over a squared minus x squared over b squared equals 1. You have to flip the x and the y because it's a difference right there. As far as it goes in principle, the A, again, just tells me the orientation. If the A, the bigger side, which we'll see when we graph it in a second, is below the x, it's oriented horizontally. If the A is below the y, it's oriented vertically. Essentially, that tells me for this one, it's oriented horizontally, it looks like that. This one is oriented vertically, it looks like that. But now, we just want to kind of work through the graph and see what's going on. And there are several key points to our hyperbola. So, we'll just go with the horizontally oriented one to start. So first off, we have 2 points called vertices. We'll do exactly what we did kind of in the ellipses. So we'll call this A0 and negative A0. And then you have the foci, which are out here. Call this C0, just like we did with the ellipse. And negative C0. And then it's the hyperbola is the set of all points in the plane such that the difference between a point and two fixed points is a positive constant. And in this case, then, the vertex is one of the points on our graph, and we go like this. And again, we get this shape that looks like a parabola, but it's really not a parabola. And we get another one on the other side. And the graph kind of looks like that. When we did an ellipse, we actually found the positive constant, the distance between any point and the two foci. And again, if you remember the math, you can look back at the old video, or if not, or look in your book. The distance was always 2a. We can do the same thing here for this one. pick any point. Let's see. Say we have this point, because that's on a hyperbola, the point A0. So let's see. The definition says the difference between two fixed points is a positive constant in xy. So the distance, say, what's the distance from this point to this point? Well, that's going to be A, and that's C, and then since we want the difference, we want this distance, that's going to be C minus A. And then we need the distance from this point to that point right there. And that point, well, this part of it is A, this part of it, it's negative C, but since we care about the distance, that's A and that's C, so that's A plus C. And since this set of all points, this difference has to be positive, this distance is clearly bigger than this distance, so we'll do the bigger distance minus the smaller distance. So A plus C minus A. And if you do that out, you get A plus C minus C plus A, distribute your negative, the C's cancel, and you get A plus A to A. Which means it's essentially defined the exact same as we did with an ellipse. The fixed positive constant is just 2A, just like it was for an ellipse. But now, much like with an ellipse, with its foci and major arc and minor arc and all that, there's a lot of properties for this hyperbola, and we want to kind of go through them all so we understand them. And I'm going to erase this just so it's cleaner. And now, let's see. First off, we have what's called the transverse axis. The transverse axis is the line, horizontal or vertical, based on the orientation, that connects the two vertices. So that's my transverse axis right there. We also have two other points. If we think about the ellipse again, we have like the major arc and then the minor arc. Or we could orient it and have the major arc here and the minor arc here. We had A and B. There's the same principle here. But, well, if this is A, we'll actually have another point B up here. And we'll just say that, for the sake of this picture, this is the point 0B, and this is the point 0, negative B. So we have the A's and the B's and the C's, just like an ellipse. But as it turns out, and again, this can be a little bit harder to see, and I'll try to do it in a different color. We'll go with the brown one. And if you look, you can actually draw, through the center of the graph, you can draw a diagonal line here, and a diagonal line right there. And essentially, both branches of this graph approach these diagonal lines right here, which we can just use to graph it. So ultimately, as we're graphing these things, we're going to want to be able to find the A's, the vertices, the C's, the foci, and the B's right here. And then we're going to want to be able to find these diagonal lines right here that tell us what the graph approaches. Because if I didn't know what the graph looked like, if I knew where these were, I could get an idea of how the branch is curved. And the only question is, how do I actually find those diagonal lines? But there's a trick. And again, I know this picture has a lot on it. The pictures in your book do too. But essentially, if I go up from here, from A, and down from A, and then I go over, my picture is not exactly straight, but pretty close. You can actually draw a box right here. And now this box gives you an indication of where those lines are, because you can find this corner and this corner, that corner and that corner, and then to find the equations of those lines, well, to find the equation of this line, you'll have this point and this point. You can do the slope-intercept formula line, you'll get your line. Same for this one. You can do this point and this point. You can get the slope between those 2 points. You can find the equation of a line. No big deal. And we know the value of this point. I'll just do this one. We can do it with all four because it's straight up from the A, or the negative A, and it's straight across from the B. So that's negative AB, this is AB, this is A negative B, and this is negative A negative B. Sorry, I just had a student come in. And from here, if we draw this box and find those corners, then I can find the equation of those lines, which will then give me a better idea of the graph. One thing I would actually stress, these diagonal lines in these boxes, I deliberately did them dotted, they're not actually part of my graph. My graph is just the set of all points in the plane such that the difference between x, y, and two fixed points is a positive constant. The actual graph is just these two branches in green. The rest of this stuff is just things that help me graph it and see what the graph looks like. Because finding these branches can be challenging. So we can find our A's, we can find our B's, that'll help us find our C's. Then we can draw the box to get the lines. And then we can just throw the branches in right there. The last thing I want to mention before I stop this, and I'm going to have to make another video where we work through some examples. For an ellipse, we had the identity b squared equals a squared minus c squared, which we said was like the Pythagorean identity, but it's not. The Pythagorean theorem that we're used to is a squared plus b squared equals c squared, and that didn't work. And the idea was, if you think about it mathematically, we use this to help us find the foci. The foci are inside of your ellipse, and if they're inside of the ellipse, you have to subtract to somehow get them. You have to subtract the A and the B to get inside of your ellipse. Well, now, these foci right here are outside of my graph. They're outside of the A and the B, which means for a hyperbola, we actually get the Pythagorean relationship a squared plus b squared equals c squared. And we can use that to kind of relate A, B, and C and do what we did with an ellipse, given 2, find the third. As far as it goes, much like with an ellipse, you can actually prove that out. I'm not going to take the time to do it all. It's in your book. But we just want to be aware of this and make sure we keep them straight. For an ellipse, you get this quasi-Pythagorean theorem. It's a difference, not a sum. Here, we actually get the sum, and then we're good to go. And like I said, I'm going to make another video where I run through some examples of this to see how it all works.